In this video, we'll discuss what it means to be Bayesian about neural networks, and we will see that, unfortunately, this is much harder than in the case of Bayesian linear regression that we saw before. Let's dive right in. Being Bayesian about neural networks. To start, let me recap the principle of what it means to be Bayesian about a simple example of linear regression that we've discussed at length in our background video on Bayesian linear regression. So if you're not familiar with this topic and you haven't watched that background video yet, I would recommend doing so, since here I only recap this topic very quickly. Now, these recap slides here are based on the book Gaussian Processes for Machine Learning by Rasmussen and Williams, and there you can also read up more details if you'd like. Now, in the case of Bayesian linear regression, we assume that our observed data is generated by a linear model with additive Gaussian noise. Now, these observations can be explained by infinitely many different models, and each of these models is more or less likely. How likely each of these models is exactly is specified by the posterior distribution, P of theta, given the data, of the linear coefficient vector theta. Now, each instantiation of this theta represents a possible linear model, as we saw in the previous slide. And we compute the posterior as the probability of this model under the prior over models, P of theta, multiplied by the likelihood of the data given this model. And then we normalize this by the so-called marginal likelihood, which is just a constant that ensures that this probability distribution integrates to 1. Now, if we assume the prior distribution of theta to be a Gaussian, then the posterior of theta is also a Gaussian, and the predictive distribution of a new data point, x star, that is also a Gaussian, thanks to Gaussians being closed under all the operations that we apply. And we can then compute the parameters of these distributions in closed form if we are given the parameters of the Gaussian observation noise and of the Gaussian prior distribution of theta. To apply the Bayesian principle to neural networks would mean to deal with all sources of uncertainty, in particular parameter uncertainty. So there is uncertainty in which weight vector explains the observed data best. And we can, of course, find the most likely one using standard SGD, but in order to quantify our uncertainty, we would rather take into account all possible explanations and weight them by their individual probability. To visualize this, here on the left, we have a standard neural network that has point estimates for each of the individual parameters, the weights. And here on the right, we have distributions for each of the individual weights. And by sampling from this joint distribution, we could then get all kinds of different weight vectors that could explain the data. While it would be nice to integrate over all possible network instantiations, in practice, we need a much more efficient solution. And one solution that we can actually get for free is to be Bayesian at least about the output layer. So the way to do that would be to first fit a standard neural network to the data, and then use a representation in the last hidden layer. So the activations in the last hidden layer for a given input x would be this phi of x, these basis functions. And then we just use Bayesian linear regression with this basis function representation. And indeed, this model was the first to enable using deep neural networks as the probabilistic model inside of Bayesian optimization. And recall that for Bayesian optimization, you actually need probabilistic predictions for the entire input range. So you don't just need a mean prediction, but you also need a variance prediction. And this approach gives you an entire predictive distribution. This approach here is also computationally quite benign, and that's very important in Bayesian optimization, since you need to fit a model in Bayesian optimization in every iteration. So it makes sense that this here was the first deep neural network model to be used inside of Bayesian optimization. Now, it is also instructive to look at the frequentist approach, the standard approach, in relationship to what a Bayesian treatment would be doing. So as before, we have our data. So these n data points, x sub I, y sub I. And we have our parameters, theta. So that's all the weights of the neural network. And then we have our prior, likelihood, and posterior. If you look at what a maximum a posteriori estimation is doing, that's actually just taking the argmax of the log posterior. And that is the argmax of the log likelihood plus the log prior. This normalization constant here, in this case, actually goes away because that doesn't actually depend on the theta that we're taking the argmax over. And if you look at this a little bit more closely, then you see that the argmax of the log likelihood here is actually just the standard cross entropy minimization. And the log prior here is actually just a regularization term. And in particular, if your prior is Gaussian, then this is actually exactly L2 regularization. And if your prior is Laplacian, then this is an L1 regularization. And actually for the even simpler maximum likelihood estimation, there you just take the argmax of the log likelihood, and there's no prior in this term here because, well, there you actually just assume a uniform prior so that the log prior here would actually be constant and not relevant to the argmax. And so this is an even simpler case. Now, if you want to do the full Bayesian treatment in Bayesian neural networks, then you want to look at this posterior here in more detail. So the posterior here is, well, the likelihood times the prior divided by the marginal likelihood. And, well, this marginal likelihood can then also be written as this integral here. And the problem here now is that this likelihood is not as simple as in linear models. For example, its mean is not a linear function of the parameters, and therefore the posterior is also not a Gaussian. And so then you actually need to look at this normalization constant, and this involves this intractable integral here. And that poses a big problem, and there's two different approaches that the machine learning community is taking in order to deal with these intractable integrals. So one possibility is to approximate the posterior distribution with a simple distribution, and that leads to variational inference. And the other possibility is to sample from this distribution, and that leads to MCMC, Markov Chain Monte Carlo. And the two next videos will be about, well, the first one about variational inference and the second one about MCMC. Now, once we have our posterior distribution over the parameters, then the prediction step works as follows. So we take our posterior distribution over the parameters, and then we multiply that with the probability of the predictions if you use these parameters. And then we integrate the whole thing over the parameters. So you can think of this as drawing a sample from this distribution here, and then making predictions with this distribution, and then doing this an infinite number of times. And so this is actually equivalent to averaging predictions from an ensemble of an infinite number of neural networks that are, each of them are weighted by the posterior probabilities of that sample. All right, so that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.